Hello everyone, welcome back to Brainy Bites. In today's video, we're going to discuss a research paper titled Tenspiler, a verified lifting-based compiler for tensor operations. This paper explores an interesting problem at the intersection of compilers, program synthesis, tensor computing, and verification. Before understanding Tenspiler, we first need to understand the problem that this paper is trying to solve. Over the last decade, we have seen an explosion in applications that require huge amounts of computation. Examples include training deep learning models, image processing, computer vision, and scientific computing. To efficiently execute these workloads, researchers and companies have developed specialized computational infrastructures. On the software side, we have frameworks such as TensorFlow, PyTorch, MLX, and XLA. And on the hardware side, we have specialized accelerators such as tensor processing units, AI accelerators, and vector processors. These systems provide powerful abstractions and optimizations that allow computationally expensive programs to run much faster. However, there is an important challenge. To take advantage of these optimizations, developers need to write their programs using the specific programming interfaces provided by these frameworks or hardware platforms. Let's understand this with an example. Imagine a developer has written a numerical application in a general-purpose language like C++ or Python. The code may contain simple loops, arrays, and mathematical operations. Now, a new tensor framework appears that can execute the same computation much faster using optimized tensor operations. To benefit from this framework, the developer cannot simply run the existing code. They have to manually rewrite the entire program using the new framework's API. And this problem keeps repeating because new frameworks and hardware accelerators continue to appear. Manually rewriting existing applications creates several problems. First, it requires significant development effort. Second, manual rewriting introduces the possibility of bugs. Third, every new framework requires a separate migration process. A compiler that translates C++ code into TensorFlow may not work for another framework, such as MLX or a hardware accelerator. Therefore, we need a way to automatically translate existing programs into different tensor-based environments while preserving correctness. Traditionally, this problem has been addressed using transpilers. A transpiler converts code written in one programming language or programming paradigm into another. However, building these transpilers is challenging. Most existing compilers rely on manually written rules. Developers need to define patterns that describe. When you see this type of code, convert it into this target operation. This approach has two major limitations. First, creating such rules requires a lot of engineering effort. Second, these compilers are usually designed for a specific target framework. A compiler designed for one tensor, DSL, may not easily support another framework or hardware accelerator. Recently, large language models have shown impressive ability in code generation and code translation. So one might ask, can we simply ask an LLM to convert normal code into tensor operations? The answer is partially yes, but there is a major problem. LLMs do not provide correctness guarantees. The generated code may look reasonable, but still contain subtle bugs. Also, LLMs struggle with less popular or newly introduced DSLs because they may not have seen enough examples during training. For systems such as compilers, where correctness is extremely important, we need stronger guarantees. This is where Tenspiler comes in. Tenspiler is a compiler that automatically translates general-purpose programs into tensor operations using a technique called verified lifting. Instead of manually writing translation rules, Tenspiler uses synthesis techniques to automatically discover an equivalent tensor-based representation of the input program. Verified lifting is a technique based on inductive program synthesis. The goal is to take an existing program and lift it into a higher-level representation, while proving that the new program behaves exactly like the original one. The process has two important stages. First, Tenspiler tries to find an equivalent representation of the input program using an intermediate language. This search process is formulated as a synthesis problem. After generating a possible translation, a theorem prover checks whether the generated program is functionally equivalent to the original program. If the two programs are equivalent, The translation is accepted and executable code is generated for the target framework. If they are not equivalent, the synthesis process continues searching for another solution. The central component of Tenspiler is an intermediate language called Tensor. Tensor is designed specifically for tensor operations. Instead of creating a separate translation system for every tensor framework, Tenspiler uses Tensor as a common representation. This is the complete workflow. Because Tensor provides a unified representation, Tenspiler can support multiple backends. Now that we understand the motivation behind Tenspiler, let's see how it actually works. Suppose we already have a C++ program that performs an image processing operation called screen blending. In this program, two images are represented as matrices. The code simply iterates through every row and every column using nested loops. For every pixel, it performs a mathematical formula and stores the result in the output image. From a programmer's perspective, this is just ordinary C++ code with loops and arithmetic operations. Nothing about it is written using TensorFlow, PyTorch, or any tensor library. Instead of directly converting this code into TensorFlow or another framework, Tenspiler performs something called lifting. Remember from the previous section that lifting means transforming the program into a higher-level representation. That higher-level representation is called Tensor. This is one of the biggest ideas in the paper. Instead of building separate translators for every tensor framework, Tenspiler first converts everything into a common intermediate language. Once the program is represented in Tensor, generating code for different backends becomes much easier. You might wonder, why introduce another language in the middle? The answer is scalability. Every tensor framework has its own API, syntax, and implementation details. If Tenspiler directly searched through TensorFlow operators, PyTorch operators, MLX operators, and hardware instructions, the search space would become enormous. Instead, Tensor ignores framework-specific implementation details and focuses only on the meaning of tensor operations. In other words, Tensor captures what computation is being performed, not how each framework implements it. This greatly simplifies the synthesis process. The paper introduces several operators in Tensor. Two important ones are tensor, abbreviated as T_T, and tensor scalar, abbreviated as T_S. Let's understand them with simple examples. The tensor operator performs element-wise operations between two tensors. For example, if we have two vectors, 1, 2, 3, and 4, 5, 6, then applying tensor addition produces 5, 7, and 9. Similarly, multiplication would multiply corresponding elements together. The second operator is tensor scalar. Instead of combining two tensors, it applies an operation between every tensor element and a single scalar value. For example, if we divide every element of a tensor by 255, that can be represented using the tensor scalar operator. Notice that these operators describe only the mathematical computation. They do not specify whether the computation will eventually run on a CPU, GPU, TensorFlow, PyTorch, or specialized hardware. Now comes the most interesting part. Traditional compilers rely heavily on manually written translation rules. Tenspiler does something completely different. It treats code translation as a search problem. The compiler asks itself, can I find a sequence of Tensor operators that produces exactly the same output as the original program? This search is formulated as a syntax-guided synthesis problem. Instead of manually specifying every translation rule, the synthesizer automatically searches through different combinations of Tensor operators. Its goal is to find one that behaves exactly like the original program. For the image blending example, the synthesizer eventually discovers a compact Tensor expression. Instead of nested loops, the entire computation is represented as a composition of tensor operations. Conceptually, the synthesized program performs 3 steps. First, it adds the two tensors together. Then, it multiplies them element by element. Next, it divides the multiplication result by 255. Finally, it subtracts this value from the earlier addition. Although this expression looks much simpler than the original nested loop implementation, it computes exactly the same result. This demonstrates one of the strengths of synthesis. It can automatically recognize higher-level tensor operations hidden inside low-level imperative code. After synthesis, Tenspiler still does not assume the translation is correct. Instead, it performs a formal verification step. The synthesis engine searches only over finite domains, meaning it reasons about a limited set of possible values. To prove correctness for all possible inputs, Tenspiler uses an automated theorem prover. In this implementation, the SMT solver, CVC5. The theorem prover mathematically proves that the synthesized tensor program is functionally identical to the original source code. If the proof succeeds, the translation is accepted. Otherwise, the synthesizer continues searching for another candidate. You might be wondering how Tenspiler verifies programs that contain loops. Loops are notoriously difficult to reason about. To solve this problem, Tenspiler automatically synthesizes loop invariants. These invariants help the theorem prover prove that the loop-based implementation and the synthesized tensor program are equivalent for every possible execution. An interesting aspect of Tenspiler is that these loop invariants are also expressed using Tensor operators. Once the Tensor program has been verified, the remaining step is surprisingly simple. Tenspiler translates the Tensor operators into the syntax of the target framework using straightforward pattern matching rules. Because every backend starts from the same intermediate representation, generating code for different frameworks becomes much easier. Instead of redesigning the compiler for every new framework, developers mainly need to define how each Tensor operator maps to the target backend. Now that we've seen the overall workflow of Tenspiler, let's focus on one of the most important contributions of this paper, Tensor, the intermediate representation that sits at the heart of the compiler. One of the biggest advantages of Tensor is its extensibility. Imagine that tomorrow a completely new tensor framework is released. With many traditional transpilers, supporting that framework would require substantial engineering effort. With Tenspiler, however, the developers mainly need to define how Tensor operators map to the new framework. The paper gives a very interesting example. The authors added support for Apple's MLX framework, which had only recently been released. They were able to do this with less than 200 lines of code. That demonstrates how flexible the Tensor design really is. Some of you may have heard about another compiler infrastructure called MLIR. It is widely used because it allows programs to be represented at different levels of abstraction. Developers can gradually transform high-level code into lower-level code suitable for different hardware platforms. So naturally, the question is, why didn't the authors simply use MLIR? According to the paper, there are two main reasons. First, the existing MLIR dialects do not contain all the tensor operators needed for Tenspiler's use cases. For example, an important select operator, which is commonly used in image processing, is not directly supported by the available MLIR dialects. Second, combining multiple MLIR dialects can become quite complicated. Tensor, on the other hand, is intentionally designed to be simple. If developers want to add a new tensor operator, they only need to describe its mathematical behavior. And if they want to support a new backend, they simply define a few pattern matching rules for code generation. Now let's look at what kinds of operations Tensor actually supports. The paper organizes these operations into several categories. Each category represents a common type of tensor computation. The first category is tensor scalar operations. These perform an operation between every element of a tensor and a single scalar value. The second category is tensor-tensor operations. Here, two tensors of the same size interact element by element. These operations are extremely common in deep learning and image processing. Another category involves reshaping tensors. The paper specifically mentions operations like transpose. Tensor also supports tensor vector products. One common example is matrix vector multiplication. This operation appears everywhere in machine learning, scientific computing, and linear algebra. Another important category is reductions. A reduction takes many values and combines them into a smaller result. One interesting feature of Tensor is that these operators can be combined recursively. In other words, the output of one tensor operation can become the input of another. By composing simple operators together, Tensor can represent surprisingly complex algorithms. Real-world programs don't only contain arithmetic operations. They also contain if statements and conditional logic. To support such programs, Tensor also includes a control flow operator called if-then-else, or ITE. Besides mathematical operations, Tensor also includes several helper functions for accessing parts of tensors. Now that we understand what Tensor is, let's see how Tenspiler actually uses it to convert ordinary programs into optimized tensor code. Let's begin with the synthesis phase. The goal here is simple. Given a normal C++ or Python program, can we automatically discover an equivalent program written entirely using Tensor operators? As we discussed earlier, this search is formulated as a syntax-guided synthesis problem. Every problem has three important components. The first is the specification. The second is the search space. And the third is the search algorithm. Let's understand each of these. The specification tells the synthesizer what kind of program it is trying to generate. For Tenspiler, the specification is very straightforward. The synthesized program must produce exactly the same output as the original source program. But instead of describing this using a collection of input-output examples, the authors use something much stronger called verification conditions. You can think of verification conditions as mathematical statements that describe what must always be true if a program is correct. For programs containing loops, these conditions usually include three requirements. First, before the loop starts executing, the loop invariant must already be true. Second, if the invariant is true before one iteration of the loop, it should still be true after that iteration finishes. Finally, once the loop completes, the invariant should guarantee that the final output satisfies the desired correctness property. Together, these conditions completely describe the behavior of the original program. Instead of guessing randomly, the synthesizer searches for a Tensor program that satisfies all these mathematical conditions. Next comes the search space. The search space defines all the possible candidate programs that the synthesizer is allowed to consider. This is represented using something called a context-free grammar. You can think of it as a set of building blocks. The grammar tells the synthesizer, you may combine these tensor operators in these valid ways. For example, it can combine tensor-tensor operations, tensor-scalar operations, reductions, transpose, control flow operators, and so on. Every possible combination generated from this grammar becomes a candidate solution. At first glance, you might think, why not simply include every possible tensor operation? The problem is that the search space grows extremely quickly. Every additional operator creates many more possible combinations. As the expression depth increases, the number of candidate programs grows exponentially. Eventually, searching becomes computationally infeasible. This is why the design of Tensor is so important. The grammar is expressive enough to represent real tensor programs, but compact enough to keep the search manageable. That balance is one of the major contributions of this paper. To perform this search, Tenspiler uses an existing program synthesis framework called Rosette. Rosette transforms the synthesis problem into a collection of mathematical constraints. Then an SMT solver searches for values that satisfy all of those constraints simultaneously. If a solution exists, Rosette returns a Tensor program that satisfies the specification. Otherwise, it keeps exploring other possibilities. Now comes the most important step. Even though Rosette has found a candidate solution, Tenspiler still does not trust it. Why? Because during synthesis, Rosette only reasons about bounded domains. In other words, it checks correctness only for a limited range of possible values. But in reality, programs should work correctly for all possible inputs. That is where the verification phase comes in. Tenspiler uses another SMT solver called CVC5. Instead of searching for a program, CVC5 tries to prove that the synthesized program and the original program are mathematically identical. More specifically, it asks the opposite question. Can I find even a single program input where these two programs behave differently? If the solver finds such an input, the synthesized program is rejected, and Tenspiler goes back to the synthesis phase to search again. If no such input exists, then the theorem prover has effectively shown that both programs are equivalent for every possible program state. This gives us a formal correctness guarantee. To reason about tensors mathematically, Tenspiler models tensors as lists using algebraic data types supported by SMT solvers. Operations like slice, take, and tail are modeled as recursive functions over these lists. This allows the theorem prover to reason about tensor computations symbolically, instead of executing them element by element. Some mathematical properties are difficult for SMT solvers to discover automatically. For example, properties like associativity, distributivity, and commutativity. Instead of expecting the solver to derive everything on its own, the authors provide additional mathematical axioms. These axioms describe how tens-YR operators behave. For example, one axiom explains how a tensor scalar multiplication can be understood recursively by multiplying the first element and then processing the remaining elements. Because tensor already works with high-level tensor operators, writing these axioms becomes much simpler and much easier to understand. This is another advantage of introducing tensor as an intermediate representation. Once the synthesized program has been formally verified, the difficult part is over. The final step is code generation. And interestingly, this turns out to be the simplest phase. Since tensor already represents high-level tensor operations, generating executable code is mostly a matter of replacing each tensor operator with its equivalent function in the target framework. For example, a tensor addition in tensor becomes torch.add in PyTorch. If the target is MLX, the exact same operation becomes mlx.core.add. Everything else remains almost identical. The code generator processes the tensor expression recursively. Whenever it encounters an operator, it replaces that operator with the corresponding function from the target framework. Suppose the synthesized tensor program represents: first, add two tensors. Then multiply them. Divide the result by 255. Finally, subtract the two intermediate results. The generated PyTorch code simply becomes a sequence of calls like torch.add, torch.multiply, torch.divide, and torch.subtract. The mathematical structure stays exactly the same. Only the syntax changes. At the time of this paper, Tenspiler already supports 6 different targets. These include NumPy for CPU execution, TensorFlow, PyTorch, Apple's MLX, Intel Gaudi's TPCC programming language, and Gemini, an open-source neural network accelerator. All of these very different platforms share the same synthesis and verification pipeline. Only the final code generation rules differ. So far, we've seen how Tenspiler synthesizes a candidate program, verifies its correctness, and finally generates code for different tensor frameworks. But there's still one important question. How can this synthesis process finish in a reasonable amount of time? Remember, synthesis is essentially a search problem, and search spaces can become enormous. So the goal is simple: reduce the search space without accidentally removing the correct solution. The paper introduces 4 major optimizations to achieve this. The first optimization is surprisingly straightforward. Instead of allowing every tensor operator, Tenspiler first looks at the expected output type of the program. For example, suppose the original program returns a 2-dimensional matrix. Then there is no reason to consider operators that produce a single integer. By removing operators whose output types cannot possibly match, Tenspiler immediately eliminates a large number of impossible candidate programs. The second optimization focuses on the inputs considered during synthesis. Earlier, we learned that synthesis only reasons about bounded program states. Now, let's understand how that helps. Instead of considering tensors of every possible size, Tenspiler starts with very small tensors. For example, during the first synthesis round, a 1-dimensional tensor is limited to only 2 elements. Similarly, integers are restricted to a small number of bits. This dramatically reduces the complexity of the synthesis problem. Of course, the resulting program is only guaranteed to work for these restricted cases. That's why the verification phase is still necessary. If the synthesized solution later fails formal verification, Tenspiler simply increases the bounds and tries again. So, rather than solving the hardest version of the problem immediately, it starts with the simplest version and gradually expands only when necessary. This is perhaps the most interesting optimization in the paper. Instead of blindly searching through every possible sequence of operators, Tenspiler first performs static analysis on the original source code. The goal is to understand what computation the program is actually performing. To represent this computation, it builds something called an expression tree. Let's look at the image blending example we've been using throughout this video. The original computation performs 4 mathematical operations: multiplication, division, addition, and subtraction. When represented as an expression tree, these operations naturally form a hierarchy. Instead of searching every possible arrangement of operators, Tenspiler simply follows the structure already present in this tree. The authors take this one step further. They replace the actual variable names and constants with placeholders. For example, instead of writing b plus a, they simply write variable plus variable. Similarly, the constant 255 becomes a generic literal. This produces something called an abstract expression tree. The synthesizer now knows the overall mathematical structure. Its remaining task is much simpler. It only needs to determine which variables belong in each position, which literals belong there, and which tensor operators best represent the computation. This dramatically reduces the search space. The final optimization is even simpler. Instead of allowing the synthesizer to invent completely new variables, Tenspiler only allows it to use variables that already exist in the original program. Likewise, constants are restricted to values that actually appear in the source code. For example, if the original program uses the constant 255, then 255 is included in the search. But arbitrary constants like 123 or 999 are never considered. Similarly, only variables that are currently live in the program can appear in synthesized expressions. This significantly reduces unnecessary choices. The combined effect of these optimizations is quite remarkable. Even for expressions containing only 4 operators, the search space contains roughly 200,000 candidate programs. After applying type-based filtering, bounded synthesis, expression tree guidance, and variable constraints, the search space shrinks to only 64 candidate expressions for the running example. That's an enormous reduction. As a result, the synthesizer is able to discover the correct Tensor program in approximately 76 seconds. Without these optimizations, the synthesis process would likely be far too slow for practical use. The paper concludes this section by describing Tenspiler's overall synthesis algorithm. Rather than performing synthesis just once, the compiler works iteratively. It starts with a small search space and small tensor sizes. Rosette searches for a candidate Tensor program and the corresponding loop invariants. Next, CVC5 checks whether the candidate is correct for all possible program states. If verification succeeds, the synthesis process stops. If verification fails, the incorrect candidate is discarded using blocking constraints, ensuring that the synthesizer does not generate the same solution again. The search then continues with a new candidate. If Rosette cannot find any candidate at all, that usually means the grammar has become too restrictive. In that case, Tenspiler expands the grammar by allowing additional operators, indexing choices, or loop structures. The process repeats until either a verified solution is found or the synthesis time limit is reached. So far, we've understood how Tenspiler works. But the most important question still remains. Does it actually work on real-world applications? To answer this, the authors evaluate Tenspiler on a diverse collection of benchmark programs covering image processing, deep learning, scientific computing, and signal processing. Let's briefly look at these benchmark sets. The first benchmark suite is called Blend. These benchmarks focus on image processing operations, particularly different image blending techniques. Image blending is a common operation in graphics software and photo editing applications. The suite contains 12 different functions, many of which use nested loops to process every pixel in an image. Since nested loops are exactly the kind of code Tenspiler targets, this benchmark is a good test of its capabilities. The second benchmark suite comes from Llama 2, Meta's open-source large language model. Instead of creating artificial examples, the authors directly extracted portions of the actual C++ inference code. These benchmarks include important neural network operations such as activation functions, attention computations, and layer normalization. This is particularly interesting because it shows that Tenspiler is capable of handling code taken directly from modern deep learning systems. The remaining benchmark suites come from well-known software libraries. These include Blaze, a widely used linear algebra library, Darknet, a deep learning framework, DSP and DSP Stone, which contain digital signal processing kernels, MathFoo, a mathematical computation library, UTDSP, Simple Array, and MakeSpear, which contains programs that manipulate integer arrays. Together, these benchmark suites cover a broad range of tensor and numerical computations. This diversity allows the authors to evaluate whether Tenspiler generalizes across different programming styles and application domains. Next, let's look at the experimental setup. The synthesis and verification phases were performed on a MacBook Pro equipped with an Intel Core i5 processor. Each benchmark was given a maximum synthesis time of 1 hour. Once a benchmark was successfully lifted into Tensor, Tenspiler generated executable code for each supported backend. The authors then evaluated the performance of the generated programs. One thing I really like about this evaluation is that the authors didn't rely on randomly generated test inputs for most of their experiments. Instead, they used real datasets. For image processing benchmarks, they used images from the ImageNet dataset. In total, the experiments used 10,000 randomly selected images from ImageNet. For the Llama benchmarks, the authors again chose realistic inputs. Instead of creating synthetic weight matrices, they used weights from Vicuna, an open-source large language model with a size similar to Llama 2. Whenever a benchmark operated on model weights, the actual Vicuna weight matrices were used. For kernels operating on embeddings, random floating point vectors were generated to simulate model inputs. Using real neural network weights makes the evaluation much more meaningful than relying on artificially created examples. Of course, generating code is only half the story. The generated programs also need to run on different hardware. To evaluate this, the authors used several hardware platforms. Each framework was executed on the hardware it was designed for. Now we've reached the most exciting part of the paper. After building Tenspiler, designing the Tensor intermediate representation, optimizing synthesis, and generating code for multiple tensor frameworks, how well does it actually perform? The authors evaluate Tenspiler from 3 different perspectives. The first experiment measures kernel performance. Kernel performance only measures the actual computation time. It does not include the time required to move data between the CPU and accelerators. This allows the authors to evaluate the computational efficiency of the generated tensor code itself. The results are quite impressive. Across all benchmark suites and hardware platforms, Tenspiler achieves an average kernel speedup of over 105 times compared to the original sequential C++ implementation, compiled with GCC using the O3 optimization flag. That's a significant improvement. When looking at individual backends, the improvements are also substantial. For example, TensorFlow achieves around 46 times speedup. PyTorch reaches approximately 244 times speedup. NumPy delivers about 26 times speedup. Apple's MLX achieves roughly 10.5 times speedup. Perhaps the most impressive result comes from Intel's Gaudi 2 AI accelerator, which reaches an average speedup of approximately 241 times. Interestingly, not every hardware platform supports every tensor operation. The paper discusses this using the Gemini accelerator. Gemini does not support some operations available in Tensor, such as element-wise tensor multiplication, slicing, and tail operations. So, what does Tenspiler do? Instead of giving up, it translates the operations that Gemini does support, while executing the unsupported operations using ordinary sequential C code on the CPU. This hybrid execution strategy allows Tenspiler to still utilize the accelerator whenever possible. However, it also means that the overall performance varies depending on how much of the program can actually run on Gemini. Another limitation is that many Gemini instructions expect square matrices. If the original program uses vectors, those vectors first need to be padded into square matrices before execution. Naturally, this increases the amount of data being processed and can reduce the overall speedup. While kernel performance is useful, it doesn't tell the whole story. In real applications, computation is only one part of the execution time. We also have to consider hardware initialization, memory management, and transferring data between the CPU and accelerators. This is what the paper refers to as end-to-end performance. When these additional costs are included, Tenspiler still achieves an average speedup of approximately 9.7 times. Although this number is smaller than the kernel-only speedup, it's still a significant improvement over the original sequential implementation. Why is the speedup smaller? The reason is fairly intuitive. Hardware accelerators are extremely fast at computation. But before they can perform any computation, the data must first be copied from the CPU to the accelerator. For small workloads, this transfer time can become a major portion of the total execution time. The paper specifically points out that the Gaudi 2 processor experiences noticeable overhead from hardware initialization and frequent transfers of small data. As a result, its impressive kernel speedups become less dramatic when looking at complete program execution. On the other hand, CPU-based libraries such as NumPy and Apple's MLX avoid much of this communication overhead because the computation happens locally without moving data to a separate accelerator. The authors also make an important observation. These benchmarks mostly involve relatively small tensor operations. Real deep learning workloads are quite different. During neural network training, large batches of data are processed together, and many computations overlap with communication. Modern systems also use techniques such as pipelining and batch processing to hide data transfer costs. So, in practical AI workloads, the communication overhead is often much less significant than what we see in these benchmark experiments. Finally, the authors compare Tenspiler against an existing compiler called Numba. If you're unfamiliar with Numba, it's a popular tool that can compile Python code to run efficiently on GPUs using CUDA. To ensure a fair comparison, the benchmark programs were manually rewritten in Python. They also had to be modified to satisfy Numba's programming model. This highlights an important limitation. Using Numba requires developers to manually adapt their programs before optimization. Tenspiler, on the other hand, works directly from the original sequential implementation without requiring these manual changes. So, how did Tenspiler perform? The results are surprisingly strong. The PyTorch and TensorFlow code automatically generated by Tenspiler runs, on average, 1.87 times faster than the GPU code generated using Numba. Why is Tenspiler faster? To understand this, the authors examined the generated GPU assembly code. They found that the code produced by Numba often missed several important GPU optimizations. For example, it did not automatically take advantage of techniques such as fused multiply-add, tile-based computation, and shared memory optimization. These are standard optimization techniques used by highly optimized libraries like PyTorch and TensorFlow. As a result, developers often need to manually optimize Numba programs to achieve peak GPU performance. So far, we've seen that Tenspiler achieves impressive performance. But another important question remains. Which of its optimization techniques actually matter the most? To answer this, the authors perform what's known as an ablation study. An ablation study is a common technique in research where you remove one component of a system at a time to see how much it contributes to the overall performance. In this case, the authors evaluate two major optimizations we discussed earlier. Let's see what happened when each of these was removed. The first experiment focuses on bounded synthesis. For this experiment, the authors removed that optimization. Instead of starting with small tensors and expanding later, they immediately used a fixed tensor bound of 4 for every benchmark. The results clearly show why incremental bounded synthesis is important. Out of the 12 blend benchmarks, 6 completely timed out. In other words, the synthesizer could not find a solution within the allowed time. Even for the benchmarks that did finish, the synthesis process became much slower. For programs involving two-dimensional tensors, the average slowdown was almost 37 times. So simply increasing the tensor bounds from the beginning dramatically increases the complexity of the synthesis problem. Next, The authors evaluate what happens if they completely remove the expression tree optimization. Without expression trees, Tenspiler no longer knows which operators are likely to appear, which variables should be used, where constants belong, or even which slice indices are relevant. As a result, the synthesizer has to discover all of these choices on its own. The grammar simply contains every possible operator up to a fixed depth. If synthesis fails, the grammar depth is increased and the search starts again. Unfortunately, this causes the search space to grow exponentially. The impact is dramatic. Without the expression tree optimization, 42 out of the total 69 benchmarks timed out. Several entire benchmark suites, including Blend, BLOS, DSP Stone, Makespear, and UTDSP, could not be synthesized at all. Even the benchmarks that eventually succeeded became much slower. On average, synthesis took more than 100 times longer compared to the version that used expression tree-based filtering. These days, there's another obvious question. Why not simply use a large language model to translate the code? The authors decided to compare Tenspiler with state-of-the-art LLMs. However, they also point out two major limitations. First, LLMs provide no formal guarantee that the generated code is actually correct. Second, they struggle when asked to generate code for new or less popular domain-specific languages. To test this, the authors evaluated Claude Opus. They intentionally selected three much less common targets: Apple's MLX, which was a relatively new framework, Intel Gaudi's TPCC programming model, and the Gemini accelerator. The task was simple. The model was asked to translate the linear Dodge benchmark from the Blend suite into each of these target DSLs. Unfortunately, none of the generated programs were correct. Let's look at what happened. For the Gemini backend, Claude generated code that partially resembled the correct API. Some function calls, like moving data into and out of the accelerator, were actually correct. However, the core computation itself was incorrect. The result for Intel Gaudi was even more interesting. Instead of using the actual programming model, the language model hallucinated an entire software library that doesn't even exist. It generated API calls for a fictional TPCC library. For Apple's MLX, the generated code came slightly closer. The model correctly identified one of the required library functions. However, the import statements were incorrect, making the entire program unusable. So far, all of Tenspiler's experiments have focused on one-dimensional and two-dimensional tensors. But this raises another interesting question. Can Tenspiler handle higher-dimensional tensors as well? To demonstrate the flexibility of their approach, the authors extend Tenspiler to support three-dimensional tensors. What's even more interesting is that the optimization techniques we discussed earlier don't need to be reinvented. Since none of the real-world benchmark suites contain 3D tensor programs, the authors created a new set of artificial benchmarks. These benchmarks were generated by combining random element-wise tensor operations. To make the comparison fair, they limited the maximum expression depth to 5, which is the same maximum depth used in their real-world benchmark suites. The experimental results are encouraging. As the expression depth increases, the synthesis time also increases. However, the increase is roughly linear. For the simplest benchmark, with an expression depth of 1, Tenspiler synthesized the program in only 6 seconds. For the most complex benchmark, with an expression depth of 5, the synthesis time increased to approximately 184 seconds. While that's certainly longer, it's still well within the 1-hour timeout used throughout the paper. The authors conclude this section by discussing how the synthesis process could be scaled even further. They suggest several interesting research directions. One possibility is to use machine learning to guide the search toward more promising candidate programs. Another idea is bottom-up synthesis, where the compiler first synthesizes the innermost loops before moving outward to larger program structures. They also propose combining bounded synthesis with loop unrolling, along with the optimization techniques already developed in Tenspiler. These ideas could make the synthesis process even more efficient when dealing with larger programs and higher-dimensional tensors. And that brings us to the end of this paper. Let's quickly recap what we've learned. The authors presented Tenspiler, a compiler that uses verified lifting to automatically translate traditional sequential programs into optimized tensor operations. The experimental results further demonstrate the effectiveness of this approach. Across 69 real-world benchmarks, Tenspiler successfully translated programs to 6 different software frameworks and hardware backends. More importantly, the generated code achieved an average 105 times kernel speedup and approximately 9.65 times end-to-end speedup, compared to the original sequential implementations. These results show that verified lifting is a promising direction for automatically migrating legacy code to modern tensor processing infrastructures while preserving correctness. If you enjoyed this paper walkthrough and found it helpful, don't forget to like the video and subscribe to the channel for more research paper explanations. Thank you for watching, and I'll see you in the next video.